Welcome to another lesson of Math 1314, College Algebra. In this section 3.4, Composition of Functions, we will discuss combining functions using algebraic operations, creating a new function by composition of functions, evaluating composite functions, finding the domain of a composite function, and decomposing a composite function into its component functions. Let's go ahead and get started with combining functions using algebraic operations. Performing algebraic operations on functions. So for a function, for functions f of x and g of x, with real numbers outputs, we can define new functions f plus g, f minus g, f times g, and f divided by g with the following relationships. F plus g of x is equal to f of x plus g of x. F minus g of x is equal to f of x minus g of x. F times g of x is equal to f of x times g of x, and f divided by g of x is equal to f of x divided by g of x, so long as g of x is not equal to 0. Let's try an example. In this example, we want to find and simplify functions f times g of x and f minus g of x for f of x equal to x minus 1 and g of x equal to x squared minus 1. Are these the same function? Well, let's see. F times g of x is defined as f of x times g of x, which, let's plug those in, that's x minus 1 times x squared minus 1. So we can double distribute those and we get x cubed minus x squared plus 1, which we can simplify and put in order of powers, x cubed minus x squared minus x plus 1. And we can also write that in fully factored form as x minus 1 times x minus 1 times x plus 1. Both of those are the same equivalent equations. Let's now try and find f minus g of x. Again, notice those are exactly the same. So f minus g of x is equal to f of x minus g of x. Again, we can plug in those functions, which is x minus 1 minus x squared minus 1. which we can distribute that negative to get x minus 1, x minus 1, plus a negative x squared plus 1, which we then can simplify to x minus 1 minus x squared plus 1, or negative x squared plus x, and we can factor out an x there if we want to get x times negative x plus 1. Now, are those two functions the same? Those functions don't look the same at all. They don't have the same values, so these are not the same function. Let's now move on and talk about composition of functions. So let's start with the definition. When the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x and functions f and g, this action defines a composite function which we can write as FOG, such that FOG of x is equal to f of g of x. So f composed with g, or FOG, the domain of FOG is all of the x, such that x is in the domain of g and x is in the domain of f. And generally speaking, g of x is the innermost function, and g is the input for f. And note that in general, f of g of x is not equal to f times g, f of x times g of x. The composition is not equal to the product in general. So, is composition of functions commutative? Well, let's let f of x equal 2x plus 1 and g of x equal 3 minus x. Let's find f of g of x and g of f of x. So f composed with g is the first one we want to find. So how do we do that? Well, f composed with g of x is equal to 2 times, and we'll plug in the value of g of x, which is 3 minus x, plus 1. 2 times 3 is 6, and 2 times negative x is minus 2x. Then we have the plus 1, which we can simplify to be negative 2x plus 7. Now let's find g composed with f, g of f of x. Well, that's equal to 3 minus f, which is 2x plus 1. We can distribute that negative to get 3 minus 2x minus 1, or negative 2x plus 2. So do we get the same value? Are f of g of x and g of f of x the same? No, they're not. Therefore, f of g of x is not equal to g of f of x, or written another way, FOG, f composed with g of x, is not equal to g composed with f of x in general, and composition is not commutative. You cannot switch the order in general. Let's try an example where we evaluate composite functions using tables, using the provided table to find f of g of 1 and g of f of 4. So how do we get started? Well, first, we need to consider the very innermost portion, which is g of 1. We want to evaluate the inner function at 1. So g of 1 is g evaluated at that x value of 1. Our x value is 1. And what is g when x is 1? Well, we look in our table. When x is 1, g of x is 3. So g of 1 is equal to 3. And then if we want to find f of g of 1, well, that's just f of 3. So f evaluated at 3. So when x is equal to 3, what is f? Well, f is also 3. So f of 3 is equal to 3. So f of g of 1 is equal to 3. What about g of f of 4? Well, g of f of 4, we need to evaluate the function f at 4. Well, when x is 4, what is f? When x is 4, f is 1. So f of 4 is 1. So in other words, when we evaluate g of f of 4, we're evaluating g of 1. So when x is 1, g of x is equal to 3. So similarly to the last time, g of 1 is equal to 3. So f of g of 1 is equal to 3, and g of f of 4 is equal to 3. So how would we go about evaluating composite functions using their graphs? How to evaluate a composite function given graphs of its individual functions. Well, the first thing we want to do is locate the given input to the inner function on the x-axis of its graph. That means taking the x value for the inner function and finding where that is on the graph. We then take the output of that function, the y value, on the y-axis, which will then inform us for the input of the outer function. So we take the output of the inner function on the x-axis of the outer function. And finally, once we've plugged in that x value into the outer function, we can then find the output of the outer function, which is the output of the composite function. Let's try an example where we use a graph to find the composition and evaluate. So using the graph, we want to evaluate g of f of 2. So the very first thing we want to find is the x value on the f graph, the graph of f of x. So we look at x equals 2. Again, f of 2. So on the graph of f, we can draw a line where x equals 2. That will help us find our output value, f of 2. Well, f of 2 happens at 5. So f of 2 is equal to 5. And then what we can do is we can plug in 5 into our outer function. So we then need to find on the graph of g of x the x value for 5. So similarly, we can draw that line at x equals 5 and see where that crosses our graph for g of x. And we see that that happens at 3. And we can draw that line there if we want to. But g of f of 2 is equal to 3. So that's how we use a graph to evaluate a composite function. Our composite function output is 3. Now that we've used tables and graphs to find and evaluate composite functions, how would we do that? Using a formula. So to evaluate a composite function using the formula, we first evaluate the inside function using the input value or the variable provided. Then we use the output of the computation as the input of the outer function. So what we then can do is find out the composite function and evaluate that using those steps. Let's try an example where we evaluate a composite function using the formula. So in this example, we're given that f of t is equal to t squared minus t, and h of x is equal to 3x plus 2, and we want to evaluate h of f of 2 and h of f of negative 2. Now notice it doesn't matter what the variables are in this case. We can still evaluate just as we normally would. So in part A, what do we do first? Well, we first want to evaluate the innermost function f of 2. So we'll evaluate f of 2, which is 2 squared, substituting 2 for t, 2 squared minus 2, which is 4 minus 2, or just 2. So h of f of 2 is the same as h of 2. So we plug in 2 for the x. So we have 3 times 2 plus 2, which is 3 times 2 is 6 plus 2 is 8. So we have that h of f of 2 is equal to 8. What about for h of f of negative 2? Well, again, we start with the innermost function and evaluate that at the value or variable given, so f of negative 2. So f of negative 2, we plug in negative 2 for each value of t, so negative 2 quantity squared minus a negative 2. Well, that's equal to 4 plus 2, which is 6. Now we plug that back into the function h, so h of 6, h of f of negative 2 is equal to h of 6. Now we can plug in 6 everywhere we see an x, so 3 times 6 plus 2 is equal to 18 plus 2, or 20. So h of f of negative 2 is equal to 20. So h of f of negative 2 is 20, and h of f of 2 is 8. You can see how those differ. So how do we find the domain of a composite function f of g of x? Well, the first thing we do is we find the domain of the innermost function, which in this case is g. Then we find the domain of f. And after we found the domain of both f and g, we find the inputs x in the domain of g, for which g of x is in the domain of f. So how does that work? Well, let's do an example where we find the domain of a composite function. In this example, we want to find the domain of the composition f of g of x, where f of x is equal to 1 over x minus 2, and g of x is equal to the square root of x plus 4. So first we want to find the domain of g of x. Well, the only place we have problems for the square root of x plus 4 is when x plus 4 is less than 0. So we set x plus 4 greater than or equal to 0, which we then can subtract 4 from both sides to get x is greater than or equal to negative 4. Now, if we were to write that in interval notation, that would be a left-hand bracket, negative 4 to infinity. Now we need to find the domain of f of x. Well, for f of x, the only place we have trouble is when x minus 2 is equal to 0. So x minus 2, the bottom part there, the denominator, cannot be 0. So we'll say x minus 2 is not equal to 0. We can add 2 to both sides of that equation to get x is not equal to 2. So the only place we have trouble in the domain of f is when x is equal to 2. So what is the domain of our composition f of g of x? Well, we want to find the values of x that cause g of x to equal 2. Can plug in the square root of x plus 4 is equal to 2, and then we can solve for x. Can do that by squaring both sides, and we get x plus 4 is equal to 4. Can subtract 4 from both sides, and we get x is equal to 0. So the only place we have problems in the composite function is when x is equal to 0. So how do we write that as the domain? So what does this mean for the domain of our composite function? Well, it means that all values of x greater than or equal to negative 4 give us legitimate values of the composite function except x equals 0. So how do we rewrite that interval? Well, it's from negative 4 to 0, not including 0, union 0 to infinity. That's the domain of f of g of x. Let's now try decomposing composite functions into component functions. Let's now discuss decomposing composite functions into component functions. Sometimes we want to decompose a function into two simpler functions. As an example, let's write f of x is equal to 4 over 3 minus the square root of 4 plus x squared as the composition of two functions. Now what we want to do is we want to look inside of this function to see if there is something in that formula that we could decompose. We want to see a function inside of a function. Well, in this one we have 4 over 3 minus the square root of some stuff, 4 plus x squared. So that's a function inside of the function. So what we can do is we can say that h of x is equal to 4 over 3 minus the square root of x, and g of x is equal to 4 plus x squared. So we can create a composition of functions where we get our original function f. So how can we do that with these two functions? Well, we can rewrite f of x as h of g of x. In other words, we can plug in the 4 plus x squared stuff, g of x, into h of x. So 4 over 3 minus, everywhere we see an x, we plug in g, so 4 plus x squared, which is the same as f as we started. So h composed with g of x is equal to f of x. Now this can be a really challenging process. Composition is a very complicated process, so you really need to practice on these and go through the homework examples and rewatch this video if you need to for additional help. Please feel free to email me if you have questions. I look forward to hearing from you, and I'll see you in the next one.